Section 7.1 is on graphing exponential functions. An exponential function is a function that has a base, or its base is a constant, and its exponent is a variable. So the big number is going to be actually a number. In the past, we've had things such as, let me show you over here, we've graphed something like f of x equals x squared. In this case, x is my base and 2 is my exponent. So my base has been a variable and my exponent has been a number. For an exponential function, your base is going to be basically a number and your exponent is going to be a variable. So x, the number that changes, is going to be up here in the exponent. Okay? And this is the form right here, f of x equals b to the x, where b is a number greater than 0. If b is greater than 1, then we're going to have exponential growth. In other words, the graph will increase exponentially, increase very fast. If b is a number between 0 and 1, then we'll have exponential decay. In other words, the graph will kind of drop off very quickly. So let's take a look at a couple examples here. We're going to start very simply by graphing f of x equals 2 to the x, and we need to state the domain and range. The way I'd like you to do this is in your calculator. So let's pull up the calculator here. Go to y equals, and this is 2 raised to the power of x. And let's take a look at what the graph looks like. And this is why it's called exponential growth, because as x increases, at a certain point it takes off and heads up like crazy, goes up very fast. This is exponential growth. The other thing that's going on here is if we were to follow this curve backwards and head in the negative direction, it looks like it hits 0, but it actually doesn't. And we'll take a look at when we take a look at the table, we'll see what's going on. The calculator can't graph it very precisely, but it approaches 0. It approaches the x-axis, but it never actually hits it. So let's go ahead and actually we can take a look here at the table. I'll make it a little bit bigger. Here's a table of values, and I have preloaded into here -6 through 4 for my x values. And you can see that when x is 0, y is 1. And when x is 1, y is 2, 2 is 4, 3 is 8. And in fact, if you notice, what it's doing is it's actually doubling. And in fact, y equals x, 2 to the x is actually a doubling function. But then it also, if we were to go the other direction, this is 1 over 2, this is 1 over 4, this is 1 over 8, this is 1 over 16, 1 over 32, 1 over 64. In other words, it keeps getting cut in half as we go the other direction. And you'll notice my y values, as I kind of move up the table here, they keep getting smaller and smaller, but they never hit 0. They get very close to 0, but they never hit 0, and they will never be negative. So let's just pick just maybe a few of these values, maybe from -2 up through +3, and put those on a table. So when x is -2, my y is 1/4. Or if you prefer the decimal, you can do 0.25. When x is -1, my y is 1/2, or 0.5. When x is 0, y is 1, 1 is 2, 2 is 4, and 3 is 8. So let's go ahead and graph those points. And when you get down to these fractions, it doesn't have to be super precise. It's just, so 1/2, -1 1/2 is going to be something like there. -1 1/4 is going to be a little bit closer to the x-axis. 0 1, 1 2, 2 4, and 3 8. And we'll draw the curve, just taking off, going up like crazy. And then as you draw it this way, it doesn't touch and it doesn't cross the x-axis. So let's identify the domain and range. So for this one, my domain is going to be all real numbers, because in this case x can be anything. I can keep getting smaller with my x's, and it's just the y's are just going to keep getting closer to 0, and I can keep getting bigger with my x's, and my y's are just going to keep getting really huge. My range, and this is where it's going to be a little bit different. So remember, range means what can y be? Well, as I go in the positive x direction, my y keeps going up, so y can be greater than something. But in this direction, my y is never hitting 0. In fact, you can even notice that from the table. So my y has to be some number that's greater than 0. It can't be greater than or equal to 0, because as you saw from the table on the calculator, it never quite got to 0. And I could keep putting in smaller x's, and it would just keep getting to be a smaller and smaller y. Okay? So this is an example of exponential growth because it's taken off real fast, and that makes sense because my base is a number that's greater than 1. The other interesting thing that's going on here is, so it looks like the curve in this direction is approaching the x-axis. So I'm going to put a little dashed line in here. And if you have a line that a curve approaches but never touches, it is called an asymptote. An asymptote. It's a line that a curve approaches but never touches. And in this case, my asymptote is the x-axis, which actually is the line y equals 0. And that makes sense that it's a line y equals 0 because, as you can see, my range is y is greater than 0. So all of my curve is going to be above that purple asymptote line right there. Okay, let's try another one. Let's graph f of x equals 1/3 raised to the x power. Okay, now notice the big difference here is, in this case, my base was 2, which is a number that's greater than 1. In this case, my base is 1/3. This is a number that's between 0 and 1, and this is actually going to give me exponential decay. So let's see what this looks like in the calculator. So I'm going to put 1/3 in parentheses and raise it to the power of x. Let's graph that. Okay, so there's my curve. Notice this, that as x gets bigger, y keeps getting smaller. So it starts very high, at a very high value, and it drops off real fast. So this is exponential decay. Let's take a look at our table. And again, this is kind of handy that I've got -6 through 4 preloaded into my x's. When x is -6, y is 729. Now I'm definitely not going to graph that, but let's go down here maybe to -2. So when x is -2, my y is 9. When x is -1, my y is 3, 1, and then actually 1, when x is 1, this 0.3 repeating is 1/3. When x is 2, 0.1 repeating is 1/9. Notice 1/3, 1/9. My next one is going to be 1/27th, and there's no way I graph that. So let's just make our table maybe -2 through 2. When you're choosing what values to put in your table, you have to kind of think about it and figure out what makes sense. So when x was -2, y was 9. X is -1, y is 3. When x is 0, y is 1. When x is 1, it was 1/3. And when x is 2, my y is 1/9. And let's go ahead and graph that. -2, 9. -1, 3. 0, 1. And these are going to be very difficult to graph, so I'm just going to kind of put them close like that. Don't worry about being very precise, except for the fact that the right-hand side of this graph is going to approach the x-axis again, but never touch it. Okay? And on the left-hand side, this is going up real fast. So again, in this case, I'm going to go ahead and draw it in, just for fun. Again, the x-axis is my asymptote. That's the line y equals 0. And my domain is all real numbers, because x can be anything. And my range, what can y be? Well, y has to be above the asymptote in this case, so y has to be greater than 0. And yes, this is exponential decay because it drops off real fast. Okay, let's try one that's a little more complicated. Here we have f of x equals 3 raised to the power of 2x, and then the whole thing minus 1. Now, be careful when you're putting this in your calculator. because what we want is 3 raised to the power of, and I'm going to put my whole exponent, 2x, in parentheses. If your calculator uses the small little number up above as the exponent, after you've put in the 2x, just make sure you use the arrow to the right to get out of the exponent, because then I want a minus 1. And let's graph that. And again, this makes sense that it's exponential growth because my base is 3, and that's greater than 1. But in this case, it looks like the graph has been dropped below the x-axis. Okay, so my asymptote's going to be something else. Let's take a look at the table. And, oh geez, look at that. I don't like what the calculator just did right here. It actually went ahead and said that when x is -5 and -6, y is -1. Technically, it is not. I think the calculator probably just can't handle that many 9s to the right of a decimal point. So what you can see is going on here is that, let's start with 0, 0. And then as we do x is 1, y is 8, x is 2, y is 80. So no way we're going to graph that. So it takes off real fast. And then in the negative direction, when x is -1, we have 0.8889. -2, 0.9877, -0.9986, -0.9998. In other words, it is getting close to 1. We are going to ignore these numbers right here, those -1s, because that's not actually true. Your calculator is just rounding it, and I don't like the fact that it's doing that. But let's go ahead and copy some of these values into our table so that we can draw it pretty accurately. I'm just going to start with -2, and that was -0.9877, -1, -0.8889. Now there's no way I'm graphing those, but we'll put them in there so you get the idea of what's going on. And 1 and 8, and 2 and 80. Okay, let's graph the points that are easy. So there's 0, 0. There's 1, 8. 280 is somewhere way the heck up there off of the computer screen. And what these are doing is they're actually approaching my asymptote, which is the line y equals -1. That's the line y equals -1. So when I draw this, I'm not going to worry too much about what those points are, but it's going to do something like that. Okay, and then take off real fast in the other direction. So my domain, again, and I think actually for most of these, is going to be all real numbers. And my range, in this case, notice the pink line is completely above the purple asymptote, which is y equals -1. So y has to be greater than -1. Okay, and let's try one more that's really kind of complicated. And thank goodness we have a calculator to do this in. So I have -1/2 times my base, which is 3/8, raised to the power of x plus 2, and then the whole thing plus 9. Now, you cannot multiply -1/2 and 3/8. That's multiplication. This 3/8 is being raised to a power. That's my exponent. And PEMDAS says do the exponents before you do multiplication. So if I were actually doing this by hand and didn't have a really nifty graphing calculator, I would have to do 3/8 raised to whatever I plug into x plus 2, evaluate that, multiply it by -1/2, and then add 9. But because I have my calculator, I can do that over here. So I'm going to use a lot of parentheses here. So parentheses, -1 divided by 2, close parentheses. That's my number out front. And now my base of 3/8 raised to the power of my exponent is x plus 2. And then this whole thing is going to be plus 9. So that's what it would look like in this calculator. Like I said before, if you have actually the ability to do an exponent as a little number up above, you're not going to need to put parentheses around x plus 2. Let's see what the graph looks like. And okay, this one is going down. So this one actually looks flipped upside down from the other ones. And it looks like I'm going to have an asymptote up here where y is equal to 9. And then the rest of my graph kind of goes underneath that. So let's take a look at the table. And you can see negative 6 is negative 16, negative 5 is very close to 0, negative 4, and then as my x's get bigger, you can see that they actually are approaching 9. So we have 8.5, 8.88, 8.92, 8.97, 8.99, and then continuing with the 8.99s. So what that tells me is that my y's are approaching 9 on the graph. So let's go ahead and copy some of that table and graph this. I think I will go ahead and put negative 6 in there, even though I can't graph negative 16.28, negative 5, negative 0.48. That's about negative 1/2. Negative 4, 5.44, so I'm going to do about 5.5 there. Negative 3, 7.67. Negative 2 was exactly 8.5. And then at this point we started to get the 8.81, 8.9. Whoops, oh, I skipped a number. Hold on. That should be 0. There we go. 8.93, and I think we get the idea here, 8.97. So this is where my y's start to approach 9. In fact, maybe I'll even go ahead and draw in my asymptote at y equals 9, because that'll make my curve a little easier to draw. Graph my points. I'm going to start with negative 5, and that's at negative 1/2. And then negative 4 is at about 5.5. Negative 3 is, let's see, 2, 4, 6, 7 plus a little bit. And then we get up to 8.5, and then we start to get really close. So this end of it is going to go like that and approach 9 but never hit there, and then this is just going to go down like that. Great. So my domain, again, is all real numbers. My range, because my asymptote is at y equals 9 and my graph is below that, it's going to be y is less than 9. Notice it can't be equal to. I didn't say that on this one, did I? No. Y has to be less than 9 in this case. So the key to doing this is graph it in your calculator, look at the table, see what values make sense, see if you can figure out what your asymptote is, because you're always going to have one side of the curve that approaches that.